In the last chapter, we talked about the marginal marine depositional environment. In this chapter, we're going to move on to the deeper part of the marine, which is the continental shelf and the deep marine depositional environments. This figure shows a cross-section of a marine environment, which includes continental shelf, continental slope, and continental rise and the deep ocean floor environment. The scale of this figure is over-exaggerated. For continental shelf, the slope of a continental shelf is only 0.1 degree, while the slope of a continental slope can reach up to 4 degrees. So on the continental shelf, we are only expecting wave and the tidal activities to dominate the depositional process on continental shelf, as well as the storm activity can play a big role in continental shelf deposition. While on the continental slope, we are expecting to see turbidity current development, and we will see deposition of turbidites. And the turbidity current continue transport to the continental rise and develop submarine fans over on the continental rise. While towards the deep ocean floor, we are only expecting to see accumulation of suspension load. The deep marine deposition will be dominated by suspension load, which is the mud deposit. This is a list of transportation and the depositional process of continental shelf. We're gonna talk about these processes one by one. So fair weather waves is a bidirectional flow, and we are expecting to see symmetrical ripples develop with this bidirectional flow. And we know that during the fair weather days in the shore phase, sediment net transportation direction is from the ocean to the sea and bringing sediments to the beach. So the second and the third swells and the storm waves, they occur during the storm weather. We know that during the storm, flow direction of the water is unpredictable. Therefore, we can have a hummocky cross stratification developed during the storm deposition. And another thing is sea level gonna increase during the storm weather. When the storm start waning, the sea level gonna drop back to its normal level. So during the storm start to accumulate the energy, that's the time that the storm waves are gonna agitate the water and erode this deposition on the continental shelf. And when the storm start waning, the wave energy gonna gradually decrease, and that's the time of deposition. And during that time, the sea level gonna start to drop to its normal level. So in the storm deposit, the sediments actually are transporting from the upper shore face to the lower shore face. Tidal deposit is a daily bidirectional flow, and we are expecting to see herringbone structure in the sigmoidal structures, and the grain size in the tidal deposit in the foreshore area from high tide to low tide area. We are expecting to see the grain size increase from mud to coarser sand from the high tide to low tide area. And the sedimentary structure is also gradually changing from lenticular flashing deposit to wavy deposit. And the wind force current, the flow direction is depending on the wind direction. So sediment plume deposit is the sediment brought by river, and the low density flow is also called hypopycnal flow. and carries a fine sediment to the offshore, while the high density flow is also called hyperpycnal flow, and it is characterized by high density with a high sediment load, and those current is following the tributaries and sometimes develop turbidites on the continental shelf. So fair weather waves, storm waves, tide and the wind as well as river sediment input are the mainly sediment source for continental shelf deposit. These pictures shows the storm deposit. So on the right, the two pictures shows the Hamakey cross stratification. And on the right, it shows the coarse-grained storm deposit, and it is also called the Temposites. So in the storm deposit, compare the upper shore face to the lower shore face storm deposit. The upper shore face is generally gonna have a coarser deposition than the lower shore face storm deposit. And also the name of Temposites is referred to the coarse-grained storm deposit, which is often seen in the upper shore face on continental shelf. And these two pictures shows the proximal storm deposit and the distal storm deposit. So in the proximal storm deposit, we see those coarse grain size and large-scale cross beddings and Hamakey cross stratification. And in the distal storm beds, we see mostly Hamakey cross laminated silts. This figure also shows the comparison of storm deposit in the shore face and the offshore. So in the shore face, the deposition of storm deposit is dominated by conglomerate and coarser sand comparing to the offshore storm deposit. And this also shows that when the storm started waning, at the beginning there's a unidirectional flow component, which is towards the shore face, offshore direction, and this indicating the transportation of sediments from the upper shore face to lower shore face and to offshore direction. And as the storm energy decreases upward, the unidirectional flow component dies out. It returned to the oscillation of wave current. And the upper shore face returned to the oscillation of the wave deposit, but sediment net transportation to landward. Now let's talk about the tidal depositional process on the continental shelf. So tidal current is a bidirectional flow, but it generates asymmetrical depositional structures, which are herringbone structures and sigmoidal depositional structures. The tidal deposition is characterized by gravity-driven current flow. The deposit during the transition from low tide to high tide is mainly sand deposit, and the deposition during the high stand of the tide will be the time for suspension load deposit. So the tidal deposit is also characterized by lenticular, flasher, and wavy deposit. On this figure, it shows from the land to the sea. We can see that on the land side, the tidal current velocity is smaller than that towards the sea. So we can see that the tidal current is driven by gravity. Therefore, as it reaches up to its highest point, the velocity will decrease, and when it's retrieved to the seawater, the velocity will increase. Therefore, there are different depositional texture and structure resulted due to this tidal current process. So at a higher level towards the land, the grain size is dominated by mud to fine sand deposit, while towards the sea, the grain size will become coarser and coarser. And the structures of deposition will also change. So at high tide, the structure will be dominated by ripples and laminations, while gradually transition from high tide level to low tide level, the structures will be changing into small dunes, large dunes, and sand ridges deposit. This figure shows the idealized sedimentary succession of the continental shelf. So in scenario A and B, it is a transgressive condition, which means the sea level is rising and the sea water depth is getting deeper and deeper, and the depositional energy is decreasing. Therefore, we see from the bottom with a conglomerate deposit, leg gravels and sand, those are from near the shore marginal marine deposit, and then transition to the tidal flat and the offshore mud deposit. And in the storm deposit, we are seeing erosional surface with a massive conglomerate deposit to hummocky cross stratification sandstone and siltstones, and then to offshore interbedded mud with a sea layer storm deposit, and to offshore mud deposit. So both of the transgressive succession of continental shelf deposit has a grain size trend of upward fining. And in the regression storm dominated shelf, which is the scenario C, we are regressive condition. It means that the sea level is lowering and the water depth of the sea is decreasing. Therefore, the energy of deposition increases through time. So we see in the succession that the depositional environment from offshore deposit transition into the shore face and the marginal marine deposit. So another thing I want to point out in this figure is that we noticed that the idealized continental shelf deposit is dominated by tidal deposit and the storm deposit. So we know that the storm weathers are rare compared to the fair weathers. But in geologic record, we are seeing much more storm deposit than fair weather wave deposit. This is because during the storms, the sediment depositional rate is much higher than the depositional rate during the fair weather. Therefore, in geologic record, we are seeing more storm weather deposits, and it does not necessarily mean that the storm weathers are more frequent in the geologic past than it is today. So how do we recognize the continental shelf deposit? So number one is a tabular shape. The tabular shape means that comparing to fluvial deposit, the thickness of the point bar deposit is decreasing to both lateral directions, and it's thinning. So the body is thick and it thins towards both ends, while the continental shelf deposit does not thin to the lateral directions. So it is a tabular shape bed. And the second says it's an extensive lateral dimension. So it also means that the continental shelf deposit has a large scale dimension and it does not thin laterally. The third is the moderate composition maturity, because continental shelf involves wave actions and it constantly washes the sediments, and therefore the sediment maturity is relatively high in the shelf deposit. And in general, the shelf deposit is well bedded. We are not expecting to see much of the massive deposit on continental shelf. We do have a certain beds of massive conglomerate deposit from storms and from turbidity current in BOMA sequence, but we don't see large-scale massive beds on continental shelf. The last 3 points is all referring to bioturbation and fossils. So to ultimately diagnostic continental shelf deposit, the strongest evidence is the marine fossils and the trace fossils. Those are the two diagnostic features that can tell us the water depth of the depositional environment. So the deep marine depositional environment, including the continental slope, continental rise, and the deep marine oceanic floor. So the depositional process within the deep marine depositional environment including the deposit, Aeolian deposit, broad suspension load. And then there's also sediment plumes that transported on the surface of the water to the inner sea and have those suspension load deposit on continental shelf, the continental rise, and deep oceanic floor. And then there's also a transportation process from continental slope towards the ocean, because the continental slope has the steepest slope. Therefore, it also there's often sediments that transported from the upper shelf on the continental from the continental shelf and then transported through continental slope deposit on the continental rise. So in this figure, it shows the sediment transportation process in the deep marine environment. So it shows that there's a wind Aeolian deposition component towards the continental slope and continental rise and the deep oceanic floor, as well as a sediment plume that contribute to the deeper marine environment. And then also similar process, we have floating ice that can provide drop stones to the deeper marine depositional environments. And then from continental and originated from continental slope, there's also density flows such as the rockfall, creep, slide, like avalanche and creep deposit. Like landslide slumps, debris flows can also transport the sediments from upper shelf to the continental slope and to continental rise. On the continental slope, the deposit will be deposit and develop a submarine fan on the continental rise. And also on the continental rise, we are also receiving oceanic current deposit, such as a contour rise. This figure shows a digital topographic model of a submarine canyon. Submarine canyon is usually submarine canyon usually serves as a conduit for sediment transportation on the continental slope to the continental rise. And the submarine canyons usually is related to a large river, so it's like a underwater extension of the large rivers. And most of the submarine canyons are found in the active continental margin. So as we previously discussed, on the deposition on continental slope and continental rise is dominated by gravity flows and the sediment transportation from the upper shelf to the continental slope and the continental rise, such as a turbidity current originated from the continental shelf and transported to continental slope and leave deposit of Boma sequence, and then most of the material transported to continental rise and develop a submarine fan deposit. On the continental rise, there's also a deposit from oceanic, and those are called contour rise. So because the oceanic current is relatively stable throughout the years, the deposition of contour rise is relatively in the large dimensional scale, and sediments are better sorted than submarine fan deposit. In this figure, the green color represents the gravity flow deposition of submarine fans on continental rise, while the yellow color represents the contour rise deposition on continental rise. These two pictures shows the contour rise deposit of continental rise. The contour rise deposition is in the largest dimension scale, and the picture on the left actually is showing the bed forms of contour rise, which is sand dunes. And on the right, it shows a cross-section of a contour rise deposit. And the contour rise, because it is formed by the fast oceanic current, therefore the contour rise has a very sharp base. The contour rise has a very sharp contact along the bedding. And these two figures shows the turbidity current deposit. And we have talked about the turbidity current and the turbidites for so many times. We're not gonna repeating that here again. And here is the Boma sequence model. And it has units from A to E. So how to recognize a deep marine deposit? The deep marine deposit is dominated by turbidites, contour rise, and deep marine shales. And the deep marine shale the deep marine sometimes also deposit massive amount of chert. So the shale in deep marine is thinly laminated and dark gray to black color. Sometimes we will see the deep marine sedimentary deposit is directly on top of the oceanic crust, which is the basalt and the ophiolite. And again, the diagnostic features of deep marine depositional environment will be the deep marine fossils and the deep marine trace fossils record.